Hi kids, this is Miss Nichols, and this week's topic is conservation of energy in waves, which was one of my very favorite bits of this unit, and there's a lot of great stuff in it. The essential question for today is, how does the principle of conservation of energy apply to waves and the energy that they carry? And we're going to be talking about at least 3 different phenomenon in which we either notice energy being conserved or don't notice energy being conserved, and why waves might sometimes be considered open and sometimes closed systems. So the first thing that's important to remember is that the wave's amplitude is the variable that is related most directly to its energy. If we're talking about a transverse wave, the up and down kind of wave, when you are talking about a low energy wave, you would draw it with very shallow, gentle jiggles, and a high energy wave would have much more dramatic ones. If you can picture real world transverse waves, like for example, using a wave on a string, or maybe a water wave, which is pretty close to transverse, you can imagine that it would take you a lot less energy to make that small wave than the amount of energy you would be required to hit the water really hard to make a bigger wave. It's true for longitudinal waves as well, like sound. If you've ever seen one of those tuning forks that musicians use to make sounds to match with their instruments, if they pluck it very gently, it's going to vibrate just a little bit. It's going to make a very quiet, low energy, low amplitude sound where you have very gentle pressure pulses. And if you pluck it more dramatically, those tines vibrate a lot and you end up getting a greater amplitude longitudinal wave. So amplitude is the only variable that we care about when we talk about conservation of energy. The frequency of the wave, that just depends on the wave source, has nothing to do with the energy. It's how many jiggles every second the person's putting into the wave. Velocity of the wave depends on the medium, and the wavelength depends on those 2 variables. So amplitude is really the key variable when we're talking about conservation of energy. So if you can imagine making a graph of the amplitude of a wave over time, for most waves, it would probably look something like that, right? You make that first original wave pulse, and as that wave travels through the medium, the wave gets smaller and smaller and smaller. So what does that tell me about the kind of system this wave is? Well, it tells you that typical waves are open systems because the amplitude is decreasing over time. That means that the wave energy is going somewhere. It's not disappearing. We believe in the principle of conservation of energy, so where is that wave energy going? Well, just like a lot of other energies that we've talked about before, that wave energy gets sucked out by these kind of natural processes. For waves, we call this damping. In damping, what's happening is some wave energy is being transformed into heat or wind, kinetic energy, gravitational energy that pushes things up and down. It can be transformed into sound as that medium is vibrating and rubbing against all the things that are nearby. So that process is called damping, and that's why things get quieter as they move further away, or waves get smaller as they get further away from the source. A couple notes about this. What is not changing as that wave moves through the medium is the frequency. Again, we're not gaining or losing these vibrations. That would be a problem as far as conservation of the number of little jiggles that are going through this medium. We can't gain or lose a vibration, an entire vibration. The velocity is also not changing as the wave moves through the medium because it depends on the medium. So even though it kind of looks like that wave is slowing down as it gets smaller and smaller and smaller, if you follow one wave pulse, you'll notice it actually moves at the same speed. If it was slowing down, the waves behind it would catch up eventually, which they never do. And that means the wavelength is also going to be constant because wavelength depends on the frequency and the velocity. If they're staying the same, wavelength must be staying the same too. So the second phenomenon in which we like to talk about how conservation of energy is relevant in waves has to do with the reflection and transmission of waves as they hit the boundary between one medium and the next. So for example, if I was outside my house trying to yell at someone on the inside, my sound wave would start in the medium of air, and then it would hit the glass, and it actually can go into that glass. Some of that sound can go into that glass, and then it can go back into air. So every time that wave hits the boundary from one medium to the next, we're going to have an interesting conservation of energy situation. You can also see this with light. If you're underwater, you know that light can go from the air into the water. So whenever wave is crossing from one medium to another, we're talking about a boundary. And the cool thing about waves hitting boundaries is that When they hit those boundaries, the energy actually splits and divides into two new waves. We treat this like a closed system. Those two new waves are going to have less energy than the original, but they are going to be able to add up to the energy of the original system. We call those waves the reflected wave. So some of the wave energy gets bounced and returns back to the first medium towards the wave source. And some of that wave energy is called transmitted, and that's the energy that goes through the second medium. The amplitude of those, as I said, is actually going to be able to be added up, just like you would do in any kind of closed system conservation situation. The bubble picture that I have below shows these two waves, right? You can see how there's some light coming from behind you, and that light is hitting the front boundary of that bubble and bouncing back towards you, and that's that reflection that you see in the bubble. But some light is also going through that bubble. The green trees that you can see in the background there, they have light bouncing off of them, and that light is passing through the bubble. So we've got both of those waves that you can kind of see in that picture of the bubble. You can probably think of some examples from your life when you've seen reflections and transmissions as well. And the third example of conservation of energy in waves is something known as interference. If you play a contact sport, you probably know interference is when two players run into each other or get in the way of each other. Interference with waves is very similar. It's when two waves coming from different directions meet in the middle of a medium. And we treat interference situations like closed systems as well, which means that the wave energy, the amplitude, is going to be combined when those two waves are overlapping. We can just add it up, just simple math. There are two different types of interference that we commonly see in the real world. One is known as constructive interference. That's when we're making a bigger wave out of two small waves. And the other is destructive interference, which is when you make a smaller wave out of two bigger waves. Constructive interference can happen anytime the original wave pulses start on the same side of the medium. So if my two wave pulses start on the top, when they hit in the middle, they're going to make an extra big up, right? So if they each have an amplitude of 1 meter, when they meet, it's going to be 2. But then those waves are going to pass through each other and continue with 1 and 1. So no matter which of those scenarios you're talking about, the total wave energy in the whole system is 2, right? 1 plus 1, 2, 1 plus 1 again. Same is true if those waves are on the bottom side of the medium. So I might have a -1 amplitude wave and a -1. When they meet in the middle, it's -2, and then we go back to -1 and -1. So that's constructive interference because we make big waves out of small waves. The other type of interference is called destructive interference, and we notice this when the waves start on opposite sides of the medium, and when they meet in the middle, the medium itself actually sort of flattens out if we're talking about this kind of transverse wave, and there is a smaller wave pulse in the middle where they meet for a short instant in time. But the waves haven't actually disappeared. The wave energy doesn't go anywhere. They will actually regenerate and continue past each other after they interfere in the middle. This is a real thing, and it's sort of crazy, and it works for all kinds of waves. So if you have ever had those noise-canceling headphones on, they're using the property of destructive interference to cancel out sound that is coming in. So a sound pulse is coming in. There's some speakers in those headphones that are playing opposite. So every time there's an up pulse, it plays a down pulse, and it actually cancels out the sound in the vicinity of your ear so that you don't hear anything. There's also ways you can cancel out light, and lots more examples if you go on to study more physics. So destructive interference and constructive interference, they're both closed systems and good examples of conservation of energy. Okay, so we're done with our big 3 examples of conservation of energy in waves. Quick little summary for you. Wave energy is shown through the amplitude of the wave. The amplitude of typical waves naturally decreases over time. This is called damping, and it basically reflects that most waves are open systems to some extent and have some wasted energy. There's a few examples in which we can treat waves as closed systems and energy being conserved. For example, when the wave hits a boundary, we can figure out how much wave energy turns into the reflection if we already know how much is transmitted, and vice versa. And the amplitude of a wave can be added or subtracted to the amplitude of another wave if they're going to interfere in the middle of a medium when they encounter each other through the process of interference. Okay, so take a few minutes now that we've gone through this and revisit your essential question, which is, how does the principle of conservation of energy apply to waves? And if you want to go a little above and beyond, maybe you can think of or research any examples that from your life or the real world where you might have noticed some of these phenomenon occurring in things that you've seen. Thanks for watching. We miss you guys.